कब स्टार्ट है?
Good morning, all.
गुड मॉर्निंग।
Right. Let's start the class. Okay, right. Now, in continuation to the yesterday's class, we have 4 topics are remained in the discussion of the R-Msc concepts. Next one is yesterday we had discussed about the Huckel molecular orbital theory. According to the Huckel molecular orbital theory, how the cyclic conjugated Poisson systems are classified into aromatic and non-aromatic. Next one, classification of conjugated cyclic conjugated systems. Okay. The screen is visible to you all?
यस सर।
Right. Classification of cyclic conjugated polyene systems. Right. Here, these cyclic conjugated polyene systems are classified in two types. One is benzenoid and non-benzenoid. Benzenoid and non-benzenoid hydrocarbons. And second one is alternate and non-alternate hydrocarbons. Alternate and non-alternate hydrocarbons. First, we coming to the first one, benzenoids and non-benzenoids. The first classification, benzenoid and non-benzenoid. The name itself indicates that the conjugated polyene systems. Yes, we know that. Do you have any doubt? You have raised the hand. If you have any doubt, you can ask me. Vinoda. No doubt? Okay. Benzenoid and non-benzenoid. Its name itself indicates that benzene or non-benzene. The hydrocarbons, cyclic, conjugated system, conjugated polyene system. Polyene system in which all the rings are benzene rings. Benzene like rings. All the rings are benzene like rings. That means 6-membered rings with the alternate double bonds. What are the benzene? Appears a 6-membered ring. A 6-membered ring. Membered ring with alternate double bonds. Alternate double bonds and a single bond. For example, you know the benzene structure. The benzene is like this. C6H6. Not required a molecular. Okay, this is the benzene. The benzene-like structures, like naphthalene. You get here. This is the naphthalene. Phenolphthalein, anthracene. The three benzene rings are fused together. Anthracene. Phenolphthalein. Next, pyrene. These are all examples for the compounds which are belongs to benzenoids. Please, Aisha, please stop the annotation. Please stop your annotation. This is called pyrene. All these molecules are belongs to benzene because all the rings are resembles to benzene. That's why these are called benzenoids. Next, non-benzenoids names itself indicate it is the name itself indicates no benzene-like structure is appeared in these molecules. Benzenoids. At least one of the ring should not be a benzene-like. Hydrocarbons. The definition: cyclic conjugated polyene polyenes with at least one ring is not a benzene ring. Is not a benzene ring. Such rings are not a benzene ring. Like that is not a six-membered ring. Six-membered ring, not a six-membered ring. Such kind of hydrocarbons are known as non-benzenoid hydrocarbons. For example, we have several examples of this. Some of them are already we've seen several molecules in the previous class. Right. Cyclooctatetraene. Next, anilines. This is 10 aniline. Next to pentylene. This is called pentylene. Next to azulene is 7-membered ring. Is fused with some 5-membered ring. This is called azulene. Now all these are non-benzenoid hydrocarbons. These are all examples for the non-benzenoid hydrocarbons. Next, second type of hydrocarbon, second type of classification. Here, alternate and non-alternate hydrocarbons. Non-alternate hydrocarbons, alternate and non-alternate hydrocarbons. When the pi centers That is, if you take the molecule, if the pi bond is there, the two ends of that pi bonds is called pi centers. The pi centers of the cyclic conjugated system are labeled as far as possible, alternatively with different spin symbols like alpha, beta, or sometimes star or without a star. During after the labeling of these all these pi centers, then observe the molecule. No two adjacent pi centers will have same spin symbol. These are also called as starable hydrocarbons, or perfectly we call it as alternate hydrocarbons. All cyclic conjugated systems contain even membered rings, that is even number of atoms in a ring, like 4, 6, 8, like even membered rings or alternate hydrocarbons. In these systems, the pi electron density is uniformly distributed over all the pi centers. For example, you take first benzene, alternate hydrocarbon. First, you take the alternate hydrocarbon. In that alternate hydrocarbons, take any molecule. So first example and the basic example is the benzene. Here I am considering, just label it. One center is two different spin symbols. It is position is alpha and beta. Sorry, just. You take the pi centers. Pi centers means the two ends of the pi bond. I forgot to. This is the one pi bond. This is one pi bond, and this is one. You consider these carbons. This pi bond is at pi carbon is labeled with alpha. This is with beta, and this is with alpha. Alternatively, you'll give the labels. Okay. Now, look at here. At any two adjacent to pi centers are not having the same spin symbol. Therefore, this kind of hydrocarbons are called as alternate hydrocarbons. Alternate hydrocarbons. This is the even number of carbons containing system. Right? Most of the hydrocarbons with the even number of carbons in their cyclic system are alternates, or simply called it as alternates. Suppose this one. Now, here instead of alpha beta, suppose you take the benzene, same benzene. These are the pi bonds. Now, at one end of pi bond is labeled with a star, and another end is labeled as unstar. And again, and the next double bond is labeled with star, leave it as unstar. That is marked as star and unmarked with a star. Now, this is also called alternatively star, alternatively unstar. Therefore, this is also called alternate hydrocarbon. This way, you can use any way. You can use the two different spin symbols or use the star and the unstar. Okay, you take here, this is the pi bond. This is labeled with star, like or alpha in symbol, unstar. Next, star, unstar, star, unstar, star, and unstar, star, and unstar. Now, look at here. At any two adjacent places of the pi centers. This is the pi center, this is the pi center, pi center, this is the pi center. All the pi centers you compare at any adjacent pi centers are having the same symbol. They are not having the same symbols. Similarly, I am labeled with the alpha beta spin symbols of the same molecule. Right. Take this pi bond, alpha, beta, alpha, beta, alpha, beta, alpha, beta, alpha, beta. Look at here. Is there any two adjacent centers are having the same spinner? same spin symbol? Either here, here. No. Therefore, these are called alternate. These 5 centers are alternatively labeled. Therefore, these hydrocarbons are called alternate hydrocarbons. Alternate hydrocarbons. Right. Now, what are the non-alternate hydrocarbons? Non-alternate hydrocarbons. Similarly, apply the same guidelines for labeling the some of the hydrocarbons. Non-alternate hydrocarbons. When the 5 systems in a cyclic conjugate system are labeled with alternatively with the different spin symbols or alternatively with the star symbol and without star symbol, then we'll get the particular arrangement of those spin symbols at any two adjacent 5 centers having the same spin symbol, that is called non-alternate. If it is no two adjacent centers have the same spin symbols are known as alternate. Here we are discussing about the non-alternate hydrocarbons. The example is pentylene is the example. The pentylene. Pentylene. Now you take the double bond. This is the double bond in the molecule. Alpha, beta, alpha, beta, alpha, beta, alpha, beta. Look at here. These two are the two adjacent 5 centers are having the same spin symbol. They're having the same spin symbol. Such kind of hydrocarbons are called non-alternate hydrocarbons. Non-alternate hydrocarbons. And another example, you take the azulene, a 7-member ring. This is a 7-member ring. This 7-member ring is fused with some 5-member ring that is called azulene. Right. It is called azulene. Just give it. Right. This is the azulene molecule. Now label them all the 5 ones. Alpha, beta, alpha, beta, alpha, beta, alpha, beta, alpha, beta. Again, this center and these two are adjacent center having the same spin. This is also, this molecule is also called alternate hydrocarbons. Okay, this is a simple classification of hydrocarbons by using this classification. Right? Next, second one is, next topic is some exceptions in the Hooke's rule. What are the exceptions? Any rule will not explain everything. Here also, Hooke's rule is having its own exception. Based on the exception, therefore it shows me some exemption. Limitations. What are the limitations? Come to the limitations of exceptions or limitations of Hooke's rule. Please note it running notes The same questions may appear in the examination. Maybe these are all important questions. Okay. Exceptions are maintain your notes, running notes. Exceptions are limitations. So Hookel rule. In the examination, the question may be appear like write the limitations of Hookel rule. Then what you write the following points, whatever the points I'm going to give the same, you need to write. Then Hookel rule was developed in 1930s. Hookel rule is developed in 1930s. Is developed in 1930s. After many years lapsed or practice on the rule, it could be put to the test to experiments. A few exceptions are being recorded by the several scientists based on that. The first limitation up to 26 annually, up to 26 annually, all annulines are obeys Hookel rule. That means based on the Hookel rule, we can classify them as aromatic or non-aromatic. Right, Hookel rule. And above 26 and above annuals, up to 26. But 26 and above annuals, or you can also call as higher annuals. Simply, I'm making it into brackets. Higher annuals, irrespective of the annuals, irrespective of the presence of 4n electrons, 4 and 5 electrons. 4 and 5 electrons are 4n plus 2 pi electrons, irrespective of 4n electrons or 4n plus 2 pi electrons are all non-aromatic. Non-aromatic. They are not shows the aromatic properties. Then this thing is not explained by the okay. But in 1965, the two scientists, one is Diwar and another one is Glacier, calculated resonance energy by using the refined methods. They found the following case. What are the things? According to Diwar and Glacier, A, the first point is that all annuals plus 2 by electrons up to 22 annuals have positive resonance energy and are aromatic. And are aromatic. Right. The second one, all anilines with 4 and 5 electrons up to 24 anilines have negative resonance energy. Negative resonance energy and are non-aromatic. Simply, we predict this a generalized statement. The anilines which are having positive resonance are aromatic. The anilines which are having non-negative charge are called as non-aromatic. Right. Next, all anilines, all higher anilines. The third point, they are concluding that like that. All higher anilines up to 24, we are they are given this these two statements up to 22, which are having the 4 and plus 2 electrons. 4 and plus 2 electrons are aromatic. Up to 24 anilines, which are having 4 and 5 electrons, are non-aromatic with negative resonance energy. Here it is the positive resonance energy, right? But above than 24 anilines, all higher anilines, higher anilines, that means above the 24, above 24 means irrespective of irrespective of 4n or 4 and 5 electrons, 4 and plus 2 5 electrons have negative resonance energy. Have negative resonance energy. Why it is having resonance energy? You recollect the definition of Huckel. What is the Huckel definition? A monocyclic conjugated polyene with 4 and plus 2 pi electrons is aromatic. Then, at the particular certain number of carbons are present in a monocyclic system that may exist in the planar ring form. Therefore, it obeys the Hooker rule. Then it shows the positive resonance energy. Therefore, it is aromatic. Or if it is a having a 4 and 5 electrons, it is showing the negative resonance energy, that is non-aromatic. But the anilines more than 24, the 26, 28, 27, 28, like that. These anilines are the number of carbons are increases, the size becomes increases. Therefore, it is difficult to maintain the planar structure. Monocyclic planar structure maintenance is not so simple. Therefore, it may be a non-planar structure. Therefore, it shows the negative resonance energy. Due to that reason, right, all the higher anilines above 24 number of carbons, irrespective of 4n electrons and 4n plus 2 pi electrons are have negative energy. Therefore, those are non-aromatic. Non-aromatic. Okay. These 3 points of explanation by the Divar and the Glacier, whatever the exemption or limitation is there, first limitation up to 24, 26 anilines are anilines obeys the Huckel rule, and above or higher anilines, irrespective of the presence of 4n or 4n plus 2 electrons, are non-aromatic. This thing is not explained by the Huckel. This limitation is explained by these two scientists, Divar and Glacier. According to them, they are taking the consideration of the resonance energy. Based on the resonance energy, the positive resonance which is having the aniline that is shows the aromatic property, and which is having the negative resonance shows the non-aromatic property. And up to 24 and 22 anilines, it will be true. And higher anilines, they are not following the Huckel rule. Therefore, most of them, all the anilines are non-aromatic due to it is showing the negative resonance energy. Okay, next limitation, second limitation. Like second limitation shown by the Huckel theory. That is Huckel's rule. Huckel's rule is of limited applicability. Applicability. It is only, according to the definition, Huckel rule is only applicable for the monocyclic conjugated polyene. Conjugated polyene. So it is explaining the aromatic property of only monocyclic systems. The monocyclic system means we are increasing the number of carbons in the only one ring systems, mono ring systems, right? It is not applicable here. Okay. It is concerned by only with the monocyclic conjugated systems. It provides no clue regarding the aromaticity of polycyclic conjugated systems. What are the polycyclic conjugated systems? We've seen that pyrene, naphthalene, anthracene is the naphthalene. Anthracene, phenanthracene. Such kind of polycyclic conjugated system. These are called polycyclic conjugated system. About the aromaticity of these kind of molecules is not explained not explained. But whenever we are extending the rule, these molecules are following the same rule and shows the aromatic property. Shows the aromatic property. Therefore, these are polycyclic conjugated system with 4 pi electrons are, some of them 4 pi electrons are but are aromatic. Some of them are, even it is having 4n plus 2 4n plus 2 pi electrons, that is showing non-aromatic. So for that, some examples I'm going to give you. That is the limitation. Second limitation is Huckel rule is only limited applicability. It is concerned only within monocyclic conjugated systems. It provides no clue regarding the aromaticity of polycyclic conjugated systems. Okay, but this is one exemption, and this exemption is also extended if some molecules, some polycyclic conjugated systems with 4 and 5 electrons, that is showing the aromatic property. Some of the polycyclic conjugated systems with 4n plus 2 pi electrons, however, it is showing non-aromatic. Look at here. The first thing is polycyclic conjugated polycyclic conjugated Just a minute. Right. Polycyclic conjugated system. Polycyclic conjugated system with 4n electrons. 4n electrons. 4n electrons, right? Then some of the molecules have, like previously also we have seen the pyrene molecule. Right. This is the pyrene. How many number of electrons are there in it? It is having 16 pi electrons. 16 pi electrons. 4, 4, 8, 4, 12, and 4, 16. Suppose 4n plus 2 pi electrons. If it is 4n pi electrons, where n is equal to 4, 4 into 4, it is 16 pi electrons. Okay, suppose the n is 4, 4 into 4 plus 2 pi electrons. How many? It should be 18 electrons. It should be the 18 electrons, then only it shows the aromatic. But in this case, it follows this rule. It is having 16 pi electrons. These 16 pi electrons, whenever it is following this rule, it is according to the Hooke's theory, it is not aromatic. It is a non-aromatic. But it is aromatic. Its property is aromatic. This is recognized by the various methods. And other is a naphthalene. Right. This is AC naphthalene. Right. How many electrons in that? 6 plus 2, 8 plus 4. How many electrons? It is having 12 5 electrons. For example, 4n 5 electron system it is. If the n is equal to 3, then you substitute it 4 into 3 into 5 electrons. Total 12 5 electrons. Suppose the same 3n value you are substituted in 4n plus 2 pi electron system, that becomes 4 into 3 plus 2 pi electron system. Then how many electrons? 12 plus 2, 14 pi electrons should have to satisfy the aromatic property. But it is having the 12 electrons. However, it is showing aromatic property, aromatic in nature. Some other examples. You take a 5-member ring. We have several examples are there. I'm going to give just the 1 or 2 examples, 3 examples. This is SN-naphthalene. Up to this, if you are SN the double bonds, that becomes SN-naphthalene. And somewhat you are extend another benzene ring, 6-member ring. Now, this is called fluoranthene. This is fluoranthene. It is having 16 pi electrons. We are already seeing the 16 how 16 pi electrons are given. If it follows the Foucault rule, it should have 18 electrons, but it is not having 18 electrons. However, it is aromatic. Okay, then this is about the first example. Next, second. In the second example, first one is completed. The second one, there are polycyclic conjugated system. Polycyclic conjugated system with 4n plus 2 pi electrons, but non-aromatic. How it is? Acetylpentane. I am taking the acetylpentane. Acetylpentane. This is the acetylpentane. How many pi electrons we calculate? Acetylpentane is having 10 pi electrons, correct? 1, 2, 3, 4, 5. 5 into 2, 10 pi electrons. It follows the 4n5 plus 2 electrons, or 4n plus 2 pi electrons rule, Foucault rule, where n is equal to 2. Then, but however it is having the 10 pi electrons or follows the Foucault rule, it is non-aromatic. It is non-aromatic. Other thing, dibenzopentanone, pentylene, sorry. Dibenzo. Right. Now I say the double bonds. 1, 2. Right. How many pi electrons it is having? 14 pi electrons. It is having 14 pi electrons. Now, it follows the Foucault rule. This is the dibenzopentylene. Right. But it is non-aromatic. Okay, these are the exemptions are shown by the Foucault rule and not explained by the Foucault rule. Okay, this is about the limitations of the Foucault rule. Now coming to Craig's rule. This is the last topic in this unit. Craig's rule. What is the Craig's rule? Who is proposed this? D.P. Craig's is the scientist, proposed a set of rules, based on the valence bond other calculations. The set of rules are framed based on valence bond, and other calculations. These rules are applied to the hydrocarbons in which alter at least two 5 centers on the symmetry axis that converts one Kekulé structure to other Kekulé structure. Suppose, for example, this is explained about the fused hydrocarbon. This is explained about the fused hydrocarbons. In the fused hydrocarbons, for example, here I am going to take one example. Based on that, I will explain. Now, you take the pentylene. You take the pentylene. This is the pentylene. In the pentylene, assign the double bonds. Right. What the Craigs will explain that these rules are applied only to the hydrocarbons in which at least two 5 centers on the symmetric axis. What is the symmetric axis? When you are inserting an axis, the axis like a line, right? The axis is I'm inserting like this. This axis will divide the molecule into two equal arms. Now, according to the in which at least two 5 centers on the symmetry axis. Two 5 centers. One of the 5 centers here and one of the 5 centers here on the axis. Like whenever we are rotating every 180 degrees, it will be converting into a Kekulé structure. Like Kekulé structure. If you take the benzene, the Kekulé structures are like this. These are the Kekulé structures. You know that what is the Kekulé structure, right? These two are the Kekulé structures of benzene. Whenever you are rotating the benzene molecule, every 180 degrees rotation, it gives the second Kekulé structure, right? Again, you are rotating, it will come to the original position, right? Similarly, here you are rotating the molecule across this axis, it generates the Kekulé structures. Based on that Kekulé structure, the 5 centers are labeled with equal number of spin symbols. Suppose here I am taking this is a 5 bond, it is labeled with alpha, it is with beta, it is alpha, it is beta, it is alpha, it is beta, it is alpha, it is beta. Look at here, this alpha center is the mirror image of this alpha center. Or it is whenever you are rotating this molecule 180 degrees, this alpha position occupies this position, this alpha position occupies this position. Okay, this beta is occupies this position, this beta occupies this position. That means you are rotating the molecule in 180 degrees across the axis. As far as possible, alternatively, we are assigning the spin symbols alternatively. The spin symbols are given to the ends of all the double bonds in the Kekulé structure. The summaries are taken the number of symmetrically related. The summaries of the symmetrically related. Sum of the number of positions which are symmetrically related. Look at here. These two are symmetrically related. Whenever you are rotating, this alpha position is occupied by this alpha. This alpha position is occupied with this one. These two are symmetrically related. These two are symmetrically related. These two are symmetrically related. Moreover, these two are having the same symmetry symbol, spin symbol. Then These are called, this is equal to the F, where F is equal to number of symmetrically related positions. Symmetrically related positions. Next, another term is there. There is a G. What is the G? Suppose whenever we are rotating this molecule, if suppose this alpha is replaced with the beta, that means one of the spin symbol is replaced with a different spin symbol, that is called G. G is the number of spins positions which are replaced with the different spin symbols on rotation across the axis during the formation of Kekulé structure.
No.
Right? Hello? Anything is there? Okay, right. Now the G in this, especially in this molecule, there is no exchanging of spin symbols on rotation. Therefore, the G is 0. G is equal to the number of spin exchanging positions or spin exchanging points. Here, the spin exchanging positions are 0 and number of symmetrically related positions are 1. This 1 is related to 1 and 2 is related to 2 and 3 is related to 3. Therefore, how many number of positions are there? F value is 3, G value is equal to 3, G value is equal to 0. Now, F plus G is equal to, if it is even number, that is aromatic in nature. If it is aromatic, if it is even, that is aromatic in nature. And F plus G is equal to odd number, that is non-aromatic in nature. Non-aromatic in nature. Right? Now, for the above one, for this molecule, F plus G is equal to the number of spin exchange position is 3. G value is equal to 0. Therefore, it is 3. Therefore, what is the number? What type of number it is? Odd number. Therefore, the molecule is non-aromatic. Non-aromatic. Right? For example, you take some other example. Yes, naphthalene you can consider it. I'm going to take naphthalene. If this example is also given in your book. This is an naphthalene. Right. Now, assign the positions alpha, beta, alpha, beta. This is the alpha and beta. Next, alpha, beta, alpha, beta. Right. This is the way you need to give the assignments. After assignments, you insert the axis. The axis is passing through these two carbon centers. These pin symbols are hidden because we are inserting the axis. The axis is passing through those two carbons. During the rotation, these two carbons are not affected. During the rotation of the axis or during the rotation of the molecule across the axis, those two carbon positions are not affected. Therefore, those two spin symbols will be not considered or neglected. Now, what is the F value? F is the number of symmetrically related positions. Symmetrically related points are this one, 1, 1, 2, 2, 3, 3. This 3 means 3 is related with 3. 4 is related to 4 symmetrical positions. Therefore, F is equal to 4. Now, G, what is the G? Whenever we are rotating this molecule across this axis, is there any spin symbol is replaced with the different spin symbol? Suppose here, in this case, we are rotating 180 degrees of this molecule. Alpha is replaced with alpha. Beta is replaced with beta. Alpha is replaced with alpha. Beta is replaced with beta. But there is no observation of alpha is replaced with beta. Okay, therefore G value is equal to 0. Now, F plus G is equal to 4 plus 0. Now, the value is equal to 4. This is the even number. Even number. The molecule is aromatic. In this way, you need to assign the aromatic or non-aromatic name or aromatic, non-aromatic nature of that molecule based on this Greg's rule. A simple rule can express the or can assign the symbol aromatic or non-aromatic based on the F plus G values. Okay, if F plus G value is even, that is aromatic. F plus G value is
Sir, excuse me.
that is non-aromatic. Okay, is there any doubt? Some voice is.
Sir, that G value, sir, how will calculate again, sir, please?
For example, I will show you this G value, right? I will give you one example to understand the G value. You take the fluoranthene. Previously also we are discussed in the aromatic and benzoate and non-benzoate, alternate and non-alternate structures. Okay. Right. What is its name? Already given in previously. Fluoranthene. FLUO. FLUORANTHE. Fluoranthene. Now, the axis is passing through. This is the axis which is passing through like this. When you are inserting the axis, that molecule should be bifurcated into two equal halves. Look at here, this axis is bifurcating the molecule into two equal halves. After bifurcation, by inserting them, after inserting the axis, now assign the spin symbols. First, I am starting with the spin symbol here, alpha, beta, alpha, beta, alpha, beta. Now here also extend alpha, beta, right? Alpha, beta, alpha, beta, right? Alpha, beta, alpha, and beta. Now, look at here. Now, you can see that what is the F value? F is equal to symmetrically related points. Symmetrically related points. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, and 7. Therefore, F is equal to 7. Next, what is the G? G is the spin exchange. If the exchange means one type of spin is exchanged with a different spin symbol. Like suppose when you are rotating this molecule, this alpha is replaced with beta. This is a spin exchange point. Here, beta is replaced with alpha. Alpha is replaced with beta. Here the same alpha is replaced with alpha. This is not no need to consider. Here beta is replaced with beta. No need to consider. Alpha is replaced with alpha. No need to consider. Beta is replaced with beta. How many are there? The spin exchange positions. One alpha is replaced with beta. This is the 1 plus beta is replaced with alpha. Two are different spin symbols are exchanging each other. Then 1 plus 1 alpha is replaced with beta. This is also position. How many there? Total
3.
3. G value is 3. Now, what is the F plus G? 7 plus 3.
10.
Now, what is that? It is
Aromatic.
simply you can understand. Okay. The same thing previous also have given this aromatic property. Look at it. Is it aromatic or not? However, it is having 4 and 5 electrons. It is aromatic. Based on the properties, actual original properties, it is aromatic, and also it is proved by the Crookes. Whatever the limitation is shown by the Huckel, that limitation is fulfilled by this Crookes explanation. Okay, this is the Crookes. Every point is important. These aromatic properties are very much important. Aromatic concepts are very much important when we are predicting the aromatic properties of drug molecules and heterocyclic molecules, right? Now, then what is the next step is 11th unit is over. This 11th unit is a total explanation part, theoretical part. Once you are thorough in this theory part, then only you can understand the all the remaining 2 chapters of the aromaticity. In the next 2 unit is unit 12, that is synthesis of some of the aromatic synthesis and properties of some non-benzenoid aromatic compounds. Already we have discussed those structures during the 11th lesson. That is synthesis, physical and chemical properties of synthesis, physical and chemical properties of non-benzenoid aromatic compounds. Non-benzenoid aromatic compounds. That means you take, we have 6 molecules or 7 molecules are there in our syllabus. 6 or 7 molecules are there. Right, what are that molecule? First one, cyclopropylene cation. The first one, cyclopropylium cation. Propylium ion. Already we seen that when we are discussing about the Huckel rule. No. This is cyclopropylium ion. And second one is cyclopentadienyl anion. Cyclopentadienium anion. That is cyclopentadienide anion. That is, it is also very important. This molecule generally seen in the metallocenes. And third one, this the part of the cyclopentadienyl ferrocenes are important. Ferrocene, the ferrocene. These are the example for the metallocene. One of the ferrous metal ion is sandwiched between the 2 cyclopentadienyl anions. Sandwiched between the negative charge. This is the ferrocene complex. And 7-membered ring propylium ion. Third one is 7-membered ring propylium ion. Why I am writing all these structures means you need to have homework. Cyclopentadienyl, heptatrinyl cation. Heptatrinyl cation it is. Next, fourth one, azulines. Fourth one, azulene is 7-member ring is fused with the 5-member ring. This is the azulene. This one is azulene. Next, fifth one, naphthalene. Sorry, anthracene. Anthracene. Sixth one is phenanthracene. These are the 3-member rings. Both are isomeric structures. Already you know that. Anthracene, phenanthrene. For all these 6 molecules, what you need to do is you need to write the 3 different syntheses. That means 3 reactions. For every molecule, you need to prepare 3 reactions, 3 different properties, 3 different chemical properties. Chemical properties. That means 3 different chemical reactions. 3 chemical reactions. Chemical reactions. Along with how it is showing aromaticity. You need to learn. That means that is explained in the physical properties. In the physical properties, there are explained dipole moment, IR, UV, NMR, and X-ray crystallography studies. X-ray studies. This is what explain IR, UV, NMR, and then the molecular features can be explained by using this one. X-ray studies data will be given that you need to read. These 3 plus 3 plus the physical properties. You have the 6 molecules are there. 6 into 6, 64 reactions and 6 molecules with physical properties that you need to prepare for the examination. Okay, that is a general normal chemical reactions and for the synthesis and chemical properties. Just simply you read it, you can understand. Okay, this is about the aromaticity. Today I am concluding this aromaticity. From next class onwards, I am going to start the heterocyclic chemistry. Later, I am going to start the natural products. In the natural products, we are going to deal with the terpenoids, alkalides. In the terpenoids, we are going to study about the Lehmann structure determination, camphor structure determination. Right. In the alkalides, we are going to discuss about the pepavariant structure determination and pinene structure determination and the general structural features of the alkalides and general structural determination reactions of the alkalides. After that, we are moving to the carbohydrates. The carbohydrate is already studied in the degree level, some amount. Only some extensions are there. Those extensions we are going to deal in that lesson. Okay, we have 6 classes are remaining. In the 6 classes, remaining 6 classes, we are going to deal in that subject. Okay. Now I am concluding the session. If you have any doubts, you can ask. Including the subject, please ask me any doubts. You don't ask me about the assignments. Those are the general things you can discuss in the groups. we will discuss about in the group. Okay, discuss in that group. But in the about this lesson, about the concept, you can ask me. I will tell you. Any doubts, please? You have 3 minutes of time. During this time, you can ask.
Sir, Huckel rule limitations.
Hmm.
How these questions can be asked on the Huckel rules?
Generally, the question is two types. One is he may be asking a direct question. Write the limitations or exceptions of the Huckel rule. That is the first type of question. In the second type of question, they may be give the name of the molecule. Suppose in the previous case we discussed the what the molecule. One molecule we are discussed in the Craig's rule, last molecule. They maybe give the name of the molecule. Now it is having 4n electrons, but it is aromatic. Why? Explain. Like that. Okay. Directly, if he thinking that he may want to give the application of that limitation, he may be asked like that. But most of the cases about the postulates and limitations, the direct question will be appear in the examination. Especially in the theory examination, direct question will be appear. Right?
Yes, sir. Yes.
Okay. Anything?
Sir, sir,
Yes.
sir, I have one more doubt, sir. Well, in like when we are forming the large ring aniline, sir,
Hmm.
that time we are presenting the monotrans like E, Z, 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 like, sir, or somewhere it is all C's.
Hmm.
How we are, sir, this nomenclature comes, that I have a small doubts.
You have when you are imagining the molecule in the 3D manner,
Yes, sir.
right? When you are imagining the 3D molecule, you need to strong enough in the cis trans and EZ classification nomenclature. Then imagine it based on the CIP priority rules. Okay. Then assign if you want to follow the EZ nomenclature, you can assign the priority rules, then assign the EZ value, EZ nomenclature. So, or when you want to assign the cis trans nomenclature, you can take the any two groups on the two carbons as the reference groups. Based on that, you can assign the cis trans. First, you need to assume that
Yes, sir.
any two groups are reference group. Based on that reference group, those two groups are same side, it is cis. Those two groups are opposite side, those two are, that is called trans.
Means, sir, whether they are
It
planar
is
or not.
always depends on your imagination. It is always depends on imagination. How you are presenting your molecule. Based on that, you need to imagine that molecule in the 3D space. In that 3D space, how this molecule is arranged. Based on the arrangement, you assign the systems or region nomenclature.
Yes, sir.
Okay.
Yes, sir.
How?
Thank you, sir.
Okay. Now I'm stopping my screen sharing. Maybe physical chemistry class starts at 1 o'clock. Okay. Accordingly, you can
Okay, sir.
join in the class. That detailed schedule will be given to you. Next week, Sunday schedule may be changed. That may be instead of 9 o'clock, the class sessions will be started at 10 o'clock. Okay. Thank you.
Good day, sir.
Thank you, sir.